Here goes. This is my presentation for class, and I'm going to present the UPSA 2021 paper by Trialisos et al. Well-typed programs can go wrong, a study of typing-related bugs in JVM compilers. And this is not quite as a bad tech day as I was having last week, and I think everything works now, hopefully, if the sound comes through and everything. All right, so the question is, how buggy are compilers anyway? And so a lot of the work in verifying compilers has been, well, that code on program optimization, it's kind of suspicious and I don't really believe it. So I'm going to try really hard to make sure it's right. On the other hand, the type checker gets a free pass. It's looking angelic there. But does it really deserve its reputation? Are you sure? Because you implemented a toy compiler for your compilers course in undergrad, but that was for a simple language. And you have actual languages these days, like Java, and they have type systems which are much more sophisticated with weird parameterized type things and bounds and everything. Is the compiler doing the right thing here? Let's find out. By the way, a comment about the paper title. It's based on an aphorism, I think, by Milner about well-typed programs cannot go wrong. And I don't really agree with it in this context, but it's a catchy title. And so maybe that's all that counts. All right, so let's find out. So what did the authors do? So first of all, let's do a brief review of type checkers. And so here you have the program and you have a type checker, and well, maybe the type checker says, yes, the program's great, you're all good. Or the type checker says, nah, there's something that's not quite right with the program. All right, so what does that mean? If the type checker says that the program is all good in terms of types, then what that means is that the program doesn't violate type safety. And so it never, for instance, reads data as the wrong type. You can make a more formal proof about this, which is beyond the scope of this class, but it's basically you have a program and then you have the programming language, and the programming language has semantics, and the proof that you can make is that a well-typed program never gets stuck in the semantics. On the other hand, if the type checker says that the program is wrong, then what that means is that there might be some execution that violates type safety. Note that it's possible to have programs which actually never violate type safety, but the type checker is actually allowed to say, I think the program's wrong, I'm approximating. That's because of the halting problem. All right, another thing that happens within the type checker is you have the program and then you have a type inference part of the compiler, and then it basically produces an annotated program with the full types, and then the type checker runs on that. And this is very useful, it alleviates the burden of writing types on the developer. And so if the developer has to write a zillion types, then they're not going to write programs in your programming language. All right, so type checkers are software. And so as with any software, they're subject to bugs. And so what are the consequences of type checking bugs? Well, they might cause the compiler to accept and compile bad programs. And so this is going back to the title. And it's like, well-typed programs can go wrong if there's a bug in the type checker. It's incorrect, I claim, in this context, because the authors are looking at compilers that compile a JVM. And so there's always the last step of the JVM, which might kill your program and throw a cast exception if your compiler does something wrong. And so it kind of goes wrong, but kind of not. It's still safe. Or the compiler might, of course, that's not true for languages like Rust, which compile directly to program code, or C++, but C++ has a type system. I don't know. Anyway, a type checking bug might also cause the compiler to reject a perfectly good program. And so, as I said, compilers are generally allowed to reject programs, but they might reject programs that the spec of the language should say that they should accept, right? So that's bad. And a third bad thing that a type checking bug can do is it can give a misleading error message on a bad program. And so that's unsatisfactory because you want the error message to lead you to the right problem. Let's try putting myself in this corner and see if that covers that stuff. All right, so what they did is they investigated 4 programmers all to JVM. So Java C, they investigated actually 2 Scala compilers, Scala 2 compiler and a Scala 3 compiler. They investigated a Kotlin compiler for mobile apps, and they investigated the Groovy compiler. All right, so they have a bug corpus, and it has 320 type checker bugs, which they found from 4 compilers that we had on the previous slide. And for each of the bugs, what they did was they looked at symptoms of the bug. So where the bug manifested, the root cause of the bug fix size, and the bug revealing tests. We'll go through these later, just to make sure I don't get it wrong now and have to start over. I'm not starting over. All right, and their observations, and observations are key to getting this kind of paper accepted, because you can collect a whole bunch of data, but if no one cares about the data, your paper is not getting in. And so what they observed was more than half the errors in the compilers that they found were failures to compile correct code. And so you have your code and it's correct, and the compiler says no. Meh. Also, they had a lot of type system implementation errors, and they mean something specific by that. They also noted that parametric polymorphism is hard, and a lot of the errors that got fixed were about parametric polymorphism. And also, you can't neglect bad code. So your test cases have to have bad code. And in fact, about 1/3 of the errors that they talked about were compiler doing the wrong thing on bad code, either compiler compiling bad code or compiler not compiling bad code as it should, but giving the wrong error message. All right, and then what do you do with this? Well, their key actionable item, and probably the reason why this paper got accepted, was that it showed that it did something useful. And so they used their knowledge in a way that they could build a program generation or fuzzing tool. And they successfully reported 28 bugs to Kotlin C and Groovy C. And by the time this paper appeared, 16 of those 28 bugs got fixed by the compiler developers. So this is always a strong argument for paper authors to accept the paper, or for reviewers to accept the paper that the authors wrote. And it's important to do good science. And so part of that is explaining what you did, which they do exhaustively, perhaps a bit too exhaustively. They also make available artifact. And so you can download their all their bugs and their classification of the bugs. So there's no secrets here. You can reproduce their work if you so desired. All right, so they state their things in terms of research questions. And so 4 research questions. What are the main symptoms of bugs? And we'll talk about that. What are bug categories based on root causes? These are 2 things that kind of seem similar, but they are quite different based on how they actually do it. And then they looked at the bug and saw what was the programming error that caused the bug. So that's how introduced, how it got fixed, and how long that code lived in the code base. And then bug revealing test cases. They looked at the bugs and checked the test cases in the bugs and tried to see what they could understand from that. We're going to start with RQ1. We're going to go in a fair amount of detail on that, and then it gets less and less as it goes on. There's also the effect of fatigue. And so in a paper, if you're writing a bunch of things, always put the most important thing first. The reader is going to have the most attention span for the first thing. And then, so you put your most compelling example first and your least compelling example last, by which case the reader may have forgotten to be critical or something. All right, so let's talk about the bug corpus. So this is what they do. This is not a great figure for a talk. It's a good figure for a paper, but if I was spending more time on a talk, I would give examples about how to do each of these instead of showing this diagram. Anyway, this is a schematic thing. And so they have the bug collection phase, BC, where they go and look at all the bug trackers for these 4 compilers and do some automatic searches based on the compiler and its bug tracker to find all of the typing related bugs for some definition all, which is pretty good. And then once they have that set of bugs, they do some filtering And so they automatically look at these bugs and exclude some bugs which don't match their criteria. And then they, in these bugs, they have for each bug manually, they find that it's a typing related bug because they know that from their filtering. And then the fixed revision, so that's linked to the compiler repository, and the test cases which are attached to the bug, and that's a condition of being included as well. So that's the collection part. And then the analysis part is where they take all the big collection, which is actually huge, it's like thousands of bugs, and then they pick up 20 bugs per compiler for all 4 compilers, and they make sure they have 20 bugs which match the criteria, and then they do the analysis on the 20 bugs, and they do that for 4 rounds of that. And so they select a sample, they do analysis, categorize bugs, and validate, and we'll talk about that. So we talked about bug collection and post filtering, but anyway, these are the 5 languages, so 2 versions of Scala, and then Java, Kotlin, and Groovy, and they have tons of bugs which pass the filters, like 1,000 for Scala 2, 1,600 for Kotlin, and then almost that for Java, and smaller numbers for Scala 3 and Groovy. All right, so the other part of their finding the corpus is having a manual analysis. And so what they did was they eventually drew 80 bugs per compiler in 4 iteration rounds. They basically drew bugs until they have 20 valid bugs per compiler per round. And then the 2 first authors of the paper independently analyzed the bugs at first so that they don't contaminate each other with information about the bug. And while doing that, they developed the categorizations. And this is a sort of grounded theory thing, which we won't really talk about too much, but it's a way of categorizing things, among other things. They discussed the bugs then to get consensus, and then additional authors of the paper then checked these bugs. All right. Papers often include threat stability. Sometimes they're good, sometimes they're not so good. But here's the ones that they mentioned. It's always good to think about whether you can come up with more threat stability. And so what's going on here is you make some sort of scientific conclusion, and then, well, is this scientific conclusion valid or not? And so obviously the bugs have to be representative. So you have to have some sort of random selection. Maybe you missed a bug category. So there's some sort of, so they did, okay, so the thing in brackets is what they did to mitigate these problems. So random selection helps with representativeness. They did a calculation to show whether they missed a bug category or not. And they're like, well, if a bug category accounts for at least 1% of bugs, then we would expect to see it this often. Are the compilers representative? And so it's 4 JVM compilers, so maybe not. And then is the analysis subjective? Well, they have a second party check and then the other check to make sure that their analysis results are somewhat valid. All right, let's talk about the bug study itself. So the main results of the paper. And so there's 4 things, basically: symptoms, root causes, how they introduced, how the bug got introduced and how it got fixed and how long it took to fix. And then some analysis of bug triggering test cases. All right, first of all, symptoms. And so it's like, how do you notice that this bug happens? And so the first type is unexpected compile time error. And so as I said, like you have their bug, and what happens? Well, sometimes the program is correct and the compiler reports an error. And so one thing I liked about this paper is it really produced an example of each thing that they're talking about. And so you can look at it and make your decision about that. You really see what kind of error they're talking about. And so this is actually a correct Kotlin program. We won't get into detail about why it's correct, but the paper does a pretty good job of explaining that. And then the compiler says, nah, there's not enough information in for type variable t, and that's incorrect. It actually can. I can't, but someone who knows Kotlin could. And so this kind of error happened a lot. So 51% of errors were these compile time errors that were not supposed to be errors. So compiler says, no, it's not supposed to. Something else that happened was internal compiler error. And so programs should never crash. Compilers especially should never crash. And sometimes they crash. So here's a Groovy example where you give Groovy, or you give some version of Groovy this program, and it crashes. it gives a null pointer exception. So what it actually does is it throws a null pointer exception, it catches that, and then rethrows it as internal compiler error. So it basically crashes. There's also assertion failures and infinite loops, which are other types of internal compiler errors. All right, we can also have unexpected runtime behavior. So the program compiles, but it gives the wrong thing. And so there's two cases of this. There's either the program was invalid and shouldn't compile, but it compiles, or the program was valid and it compiles, but then there was some method call which is incorrectly resolved. This example is a Java example where the program is fine, the compiler is wrong, so that sucks, right? It's like you expect your compiler to be right and you're very disappointed if it's not. So it compiles, but then you try to run it and it gets a class cast exception. You're like, WTF, that shouldn't happen. If it wasn't Java VM, then you could actually have like memory corruption errors because it could compile something, it could have a method call and it calls the wrong thing. In this case, JVM is going to make sure nothing actually terribly bad happens except that the program crashes, which is not great, but it's not terrible. And the other thing is the compiler tells you the wrong thing. So error messages, right? You expect the error message to be right, and sometimes the error message is wrong. In fact, in this case, this really simple program, it gives two error messages, which are contradictory. One of the error messages is correct, and the other one is not correct. Oh well. All right, so that's the types of symptoms. Oh, oops, there's one more, which is compilation perf, which is closely related to crash, but is perf error. So you might accidentally put an exponential in your compiler, and there's 26 things, or A2W is not 26, 24 things, I think. And so it takes like 2 to 24 time, and that's a long time, right? So it doesn't crash, but it might as well crash, or it might as well loop, infinite loop. It's basically an infinite loop. This is 2% of errors. All right, they have some analysis of the symptoms. It's not particularly elucidating. I kind of had wished that they had said some deeper analysis of the symptoms, but they didn't. All right, the next thing is root causes. And so we talked about how you could see the error. Now we'll talk about the root cause of the error, which is kind of nice. And so basically they did a manual categorization. And so they said 129 of the errors were type-related bugs, which is most of it for the type checker, which kind of makes sense. Then semantic analysis and resolution accounted for 77 of the bugs. These, of course, are not exhaustive because you'll see that adds up to more than 320. Resolution is like, virtual method resolution. So you have O.F, but it's like, it says O has the wrong thing in it. Yeah, it's wrong. Error handling is actually hard, but it surprisingly accounts for only 22 of the errors. And then Scala does a lot of ASC transformation, and that's tied in with the type checker. And so that accounts for 15 of the bugs. And so, well, I guess part of this, what this paper is pointing out is, reasoning about types is hard. And so we have these bugs, and these bugs are because reasoning about types is hard. Okay, so it helps with the thesis of this paper. Okay, fine. They did some per compiler analysis. And so Java C had more error handling bugs. They didn't say why. Maybe it's too hard to say why, but I was kind of disappointed about that. And then in Scala has more AST transformation. So you have some feature interaction bugs where you have two compiler features and they don't interact nicely, and then you get a bug, boom. All right, the next part of their study is how introduced, fixed, how long. And so what they did was they investigated fixes to classify these fixes among logic errors. So for instance, a missing case, so you have an if but not an else branch. So then the fix is you introduce an else branch. Algorithmic errors, so you have some sort of implementation, but it's a wrong implementation. It's not just the logic error, you didn't forget something. It's like you use the wrong data structure, and that data structure doesn't have the property you want. And then the worst is language design errors. And so the language is wrong. You have to fix the language, and you're writing your compiler. Sometimes you have to fix the language and get your fix approved by the language, the people who own the language. The logic errors were reasonably local to fix, right? So it's just a method or one file. Algorithmic errors, they said, were fixed within a reasonably small scope, but not as small. Then language design errors can be huge. I mean, you have to redesign the language specification, right? And so that can be potentially quite large. This doesn't show how these fixes compared with the types of fixes we talked about, but that's a graph that shows, how big the fixes are. And so 40% of the bugs required 10 lines of code or less to fix. Then almost 90% of the bugs required 100 lines of code or less to fix. So they're mostly pretty small. But they said there was one large 3,000 line of code that fixed that was basically one of the language design fixes. When you say something, you got to give context, right? And so they didn't really give context about how this compared to other domains. I mean, I think it's probably the case that most bug fixes are going to be like that as well. And so I was a bit disappointed that they didn't talk about that. And then how long lasting were the fixed bugs? So you have this bug and you fix it. Was it a 2-week bug between reporting and fix, or was it a 2-year bug between reporting and fix? And so, half the bugs are fixed in like 3 weeks. And then there's this, of course, really long tail. Some bugs take like 3 years to fix, especially in Scala, C, and Dotty. The last thing they did was they investigated bug triggering test cases. And so this is another way, it's kind of like symptoms, but it's kind of not. It's like, well, what features of the test cases are important when you have a bug, when you have a type system error, right? And so mostly it's like parameterized types. Parameterized types are hard, parameterized classes, functions, and bounded type parameters. I guess it's also not just that they're hard, but also that they're really common. And most Java code these days involve parameterized types, right? Whereas parameterized functions are much rarer. Like you might use that sometimes, but it's not all the time, right? And, but OOP features are also quite common too, right? And so you would also expect that to be a lot. So I don't know how much this has to do with like how hard these are actually to implement in terms of type checker versus how much they are going to be encountered by programmers. I don't know. All right, so a key part of this paper, and the only way it gets accepted is by having a good lessons learned and by having good actionable outcomes, right? So what they learned was if you want to find bugs, you have to have both valid and invalid programs per each symptom, and you generate separately the valid programs and invalid programs. They found a lot of type-related bugs in the type limitations. You find parametric polymorphism is involved in a lot of bugs. Standard library is involved in a lot of bugs. Control flow and arithmetic are uncommon. And then in Scala, implicits and pattern matching are hard. Is this surprising? It's not that surprising, but it does support the thesis. So, okay. And it's things that we didn't know before and that are relevant to some people, especially compiler writers. All right, the actionable outcome is a fuzzer. And so they wrote some code which generates an intermediate repetition IR. And then from this IR, they generate Kotlin and Groovy code, targets parametric polymorphism, and forces use of the inference in the compilers by skipping some annotations. It generates programs which are valid by construction, and it finds 28 previously unknown bugs. So what they concluded was first of all, based on their corpus of 320 typing-related compiler bugs, they studied symptoms, root causes, what was needed to fix these bugs, and the test cases that are attached to the bugs. And you can use this for test case generation. All right, so what I want you to do when you talk about a paper also is to have thoughts and questions about the paper. And so you can have your conclusions as opposed to the author's conclusions. And so my opinion is, yeah, this is a fairly exhaustive analysis of bugs in this domain. I mean, it obviously didn't analyze all the bugs, but what I mean is that they were pretty thorough and they analyzed a lot of bugs. So the N is large enough for something where you're doing quite a bit of manual analysis. The paper is interesting to compiler writers and language designers. So it's like, so what? Well, if you're writing a compiler, maybe you want to know this is something that you should actually care about. As I said before, in a JVM context, you're protected by unsoundness by the JVM. In my version of the paper, I wrote why a couple of times. I said so sometimes. But one way I read papers when I really want to understand the paper is actually have a printed version of the paper and I read it and I annotate it. And for me, maybe I'm old, but I just do that on paper. And so there was a couple of whys throughout. So that some things were sort of unsatisfying. In a discussion, I will pull them out and we can maybe talk about them. And the actual outcomes are a vital part of the paper. In the end, what is this paper? I mean, I think it contributes a useful piece of knowledge, and I think it's good for us to talk about in terms of an empirical study. It's a lot of work. It's certainly, I wouldn't do this as a course project at this scale because it's just too big, but it's a worthy contribution and is something that was probably worthy of being at UPSA. All right, that is all I have for this paper, and I look forward to discussing with it soon. Great.